Alright, now let's talk about color absorptivity and how this ultimately relates to Beer's law. Now I wish I could claim to have made this slide, but note the citation at the bottom. I just made a couple of little notes and I'll try to describe it and how it relates to what we're going to be talking about in this class, but it's a very, very nice and well-made slide. I wish I could claim it as my own. First, I'll direct your attention to these two samples. They are both copper-based solutions, but one is just copper with water, and this darker blue chemical solution is copper with ammonia. In fact, this is the same type of solution that I prepared in the previous video. And over here for reference is our color wheel in case you don't remember it. This is data taken on a UV vis spectrophotometer like the one that I showed you before of each of these samples. And here is our electromagnetic spectrum, or at least the visible portion, for reference. The data for the copper-ammonia complex, which is what we're first going to look at, is rather similar to the data that I took earlier. What it's showing is the absorbance of light at different wavelengths in the visible light spectrum. And what it's showing us is that there is little to no light absorption at these wavelengths here, which correspond to blue and purple light. By the time we get to 500 nanometers, which is closer to green, we're starting to get light absorbance, but not that much compared to these other wavelengths, which correspond to yellow through red, with peak absorption happening at around 610 nanometers, which corresponds to orange light. And so these three colors aren't well absorbed by this solution, and so they're able to transmit through and reach a person's eye. Now, if the other colors were also able to transmit through, they would cancel out these three, and we would see a colorless solution. However, that's not the case, right? We see that the other colors are absorbed, especially orange, which is blue's counterpart. And so that's why of the colors that do make it through the solution, the blue winds up dominating, because the color that should be canceling it out is the most absorbed, as we can see here. And so to relate this to our earlier absorptivity concept, we would say that this solution here has a maximum absorptivity value for this particular wavelength of light. That particular wavelength of light must have an energy that is equal to the delta E between energy levels in this chemical. On the other hand, this wavelength of light must have an energy that's not even close to being equal to the delta E, which is why the absorptivity for this particular wavelength of light is effectively zero, hence this sample doesn't absorb that wavelength. Now this sample also doesn't absorb that wavelength. In fact, it doesn't absorb the green wavelengths at all either. It doesn't start absorbing until we reach the orange part of the spectrum, and so a significant amount of orange light is able to make it through the sample along with the blue light. And so a fair amount of that blue light is canceled out by the orange, so notice it's nowhere near as intense or dark of a blue as over here. Furthermore, this particular sample absorbs red light far more strongly than the orange light, and red light is green's opposite. And so the green color is able to make it through strongly, and its canceling out complementary color is not. And so there's a lot more green in this solution, as we can see, compared to this one. And it's worth quickly noting that this chemical's maximum absorptivity is for a wavelength of light that is not in our visible spectrum. That's where the infrared or IR part of the electromagnetic spectrum begins. So this is where colors that we've been learning about since elementary school are starting to meet with college-level analytical chemistry. Let's make some quick notes. Let's label this part absorption spectra and color. Absorption spectra and color. Absorption spectra being these plots of absorbance versus wavelength, as we shine in different wavelengths of light. And as for color, let's start by noting that white light contains all colors. White light contains all colors. And a substance is colored when some light is transmitted or reflected and some is absorbed. Substance is colored substance is colored when some light is transmitted or reflected, slash reflected. We'll get into the difference momentarily. When some light is transmitted or reflected and other light is absorbed. Other light is absorbed. The transmitted and reflected light is what we see, colors we see, and the light that is absorbed are the colors that we don't see. Colors we don't see. In particular, the color that we primarily see is the opposite of the color that is most absorbed. Like in that previous slide, the most absorbed color of one of those solutions was orange, and so the color we primarily saw was blue, its opposite. Now, many of you may have already come into this class knowing this counterintuitive concept, where the color that you see is the opposite of the color that's most absorbed by a substance. But typically when you learn about this idea, you learn it in the context of solids, which means you come into this class with a misconception, which is that you think that the color that you're observing is the one that's reflected the most. That is true for solids. For example, this red stripe on my sweater is reflecting red light more than any other color, while it's in turn absorbing more green light, the opposite color. And so white light's coming in, all colors hit the sweater, red light bounces back the most, green light is absorbed the most. But we're not measuring solids in this class, we're doing solutions, which are more liquid in nature, right? And so this red solution right here, it's not reflecting red light, it's transmitting it. So white light's coming in from the other side, the green is trapped inside, while the red transmits through and reaches your eye, or the camera in this case. Okay, and this goes with what we already understand about liquids and solutions, like with just simple water here. We can see my finger from the other side of this glass because the light coming off of my finger is transmitting through the water, no problem. Whereas if I hold my finger on the other side, you can't really see the reflection of my finger, right? Liquids, they do reflect light, but very faintly. They transmit it a lot more strongly. That's why those earlier equations related absorbance to T for transmission rather than R for reflection. Now I'll end this video by showing you a clicker. This one, I'll warn you, is rather difficult, so feel free to take a crack at it now, but we'll do it in Zoom.